Section 3.4 is actually broken into two groupings in your course notes, but it begins on page 25 of your course notes. The first portion we're going to look at is 3.4a, definition of a derivative. It says the derivative of a function denoted as f, this reads prime, f prime of x, or so the derivative of x represents the instantaneous rate of change as a function. The instantaneous rate of change. So the same thing we evaluated in section 3.3 is also the derivative. It also represents the slope of a graph at a specific point x. So the instantaneous rate of change, same thing as the slope at a specific point, is the derivative of a function. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h, as long as the limit exists. Of course, the limit doesn't always exist at a specific point. Like the last section, there is an alternate form. The limit as b approaches x of f of b minus f of x over b minus x. And like I mentioned in the last section, this is the equation we're going to use most frequently. So it's very similar to the last one, except now we're just writing it slightly different. So we're using f of x instead of the a plus h portion. So an example. The last slide said this would equal, so f of prime of x would equal the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so in this case, applying that to this function, we want the limit as h approaches 0. Now we're going to plug in x plus h in for our x. So we would have 1 minus x plus h quantity squared minus f of x. So minus the function as it's given to us, divided by h. Okay, so now we need to FOIL x plus h. So if you still need to, make sure you do that. Review this. X plus h squared is equal to x plus h times x plus h. So we get x squared plus 2xh plus h squared. So the limit as h approaches 0 of 1 minus the value we just found, the square of x plus h, minus 1 minus x squared. So let's distribute that negative to each of these terms. We get minus 1 plus x squared over h. And so this first term, we still have to distribute that negative out front. So h approaches 0. We must distribute this negative to each term in the parentheses. So we get 1 minus x squared minus 2xh minus h squared minus 1 plus x squared, all divided by h. Okay, now generally speaking, and it's true for this problem, many of our terms will drop out. So the x squareds will be gone, and the 1s will be gone. So we are left with, I'm going to write it in descending order, negative h squared minus 2xh over h. And like in the last section happened in one of our examples in 3.3, all of these terms have an h in common. So we can cancel out the h in each of them. We get negative h minus 2x. Okay? Now our rule says this is a polynomial, right? H is a number approaching 0. So we can simply plug in 0 for h and simplify. So our limit is negative 2x. So notice this is not just simply a number, but a value determined by x. So it's at a specific x value, this is the slope. Now that does make sense. If we look back at our original function, f of x equals 1 minus x squared, that is not a line, right? So it's actually a parabola facing downwards, so we know the slope is not constant throughout it. It must be changing at different points. So it makes sense that it's not just a numeric value, but it depends on x. Okay, now this chart tells us a little bit about the difference between the quotient and the derivative. Okay, so this first, the left side of the chart says f of x plus h minus f of x over h. That's the average rate of change, not the instantaneous rate of change. So notice right here, the left chart is the average rate of change, and the right chart is the instantaneous rate of change. So the left chart is the slope of a secant line. If you remember a secant line, let's draw something real quick. A secant line is if we pick 2 points, this line goes through it, right? So that's also the average rate of change of the graph between those 2 points, okay? The difference quotient is also called the average velocity. Velocity is a change as well, right? How much we're changing a specific point. So the difference quotient is equal to the average velocity, whereas the derivative is equal to the instantaneous velocity. I should mention also, so this is a secant line, okay? A tangent line, as is mentioned here, a tangent line is something like this. So we pick a value. It is the instantaneous rate of change at that point. So the tangent line touches the graph at that point, okay? So the difference quotient is also equal to the average rate of change in cost, revenue, or profit, average rate being the keywords. And then the derivative is equal to the marginal cost, revenue, or profit. So at a specific point, okay? So a derivative is much more specific than the difference quotient, which is the average or the big picture as opposed to the specific values. The left side of this chart. So f of x plus h minus f of x over h. We're not finding the limit, okay? H was in this equation, okay? Now, h in this equation is equal to b minus a, okay? So we also saw a average rate of change equation, and that is the same thing as this. So we can also go back and use f of b minus f of a over b minus a. And okay, so another example for us. Example 2. Find the equation of the secant line through the points where x has the given values and the equation of the tangent line where x has the first value. Okay, so for part A, we're looking for the equation of the secant line, which is, so for part A, f of x plus h minus f of x over h. Now I realize at this point that we didn't define what might make more sense when you're looking at this problem, okay? So let's actually substitute this. Let's go back to our average rate of change equation. F of b minus f of a over b minus a. It really is the same thing. Okay, so we're going to plug in 16 for B. Okay, this is our B, and 9 is our A. So we have f of 16, plug in 16 into the function, minus f of 9, plug in 9 into the function, over 16 minus 9. And we should get 4/7. Pause and double check to make sure you get that. So that is the slope of the secant line. Okay, this is the slope of the secant line. Now, if we go back and read the question, it says find the equation of the secant line. So right now we just have a slope, okay? So in order to find the equation of a line, we need an x and y value, right? Either of these values of x will work, okay? Because the secant line is going to go through both of these points. So if x is equal to 9, then plug that into the function, and we get y is equal to 12. Okay, so we have an x value, we have a y value, we have a slope. We can use our point slope form of our equation to find the equation of the secant line. So we would get y minus 12 equals 4/7 times x minus 9. We want to distribute our 4/7. And if we add 12 to both sides, we get 48/7. Okay, now part B says find the equation of the tangent line where x has the first value, x equals, or the equation of the tangent line where x is equal to 9. So we have f of x equals 4 square root of x, and we want to know the slope. So we are going to use the limit as h approaches 0. H approaches 0 of f of x plus h minus f of x over h. Okay, so this is the derivative at that point. Okay, the derivative is also equal to the slope of the tangent line. So if we apply this to our specific function, we are looking for the limit as h approaches 0 of f of x plus h. So we are plugging in x plus h instead of x. Okay, now I should backtrack a minute, right? Because we are saying x is equal to 9. We want to know it when x equals 9. So let's stop and let's actually plug in 9 instead of x. So my equation instead of x should have a 9. So 4 times the square root of 9 plus h minus f of 9, so minus 4 times square root 9 over h. Okay, so let's simplify this. Okay, so to simplify this, we want to multiply by the reciprocal of the numerator. So to get rid of our radicals in that numerator. So first, we do see that we have a 4 in each of our terms. So let's factor that out. Factor out the 4. And then let's multiply numerator and denominator by the reciprocal of this. So square root of 9 plus h plus square root of 9. Again, do that in the numerator and in the denominator. As long as we are multiplying by the same thing in the numerator and denominator, we're multiplying by 1. Okay, now as you will see, that really helps us simplify this. So in the numerator, we still have a 4 out front, but when we multiply this, the radicals go away, right? Square root of 9 plus h times square root of 9 plus h is simply 9 plus h. Our outside terms and inside terms cancel out, and we get minus square root of 9 times square root of 9, or minus 9. And in the denominator, we will just we will just leave it as it is. Okay, now when we simplify the numerator, inside the parentheses, the 9's cancel out. So we simply have 4 and h left over. And we still have the h in the denominator, which we can see now will cancel with the h in the numerator. Those cancel. So we have the limit as h approaches 0 of 4 divided by square root of 9 plus h plus square root of 9. Okay, of course, square root of 9 is simply 3. So if we plug 0 in at this point, we will get the limit as h approaches 0 of, no, we're plugging in the value. We don't need the limit anymore. So if we plug in to this polynomial function, 0 in for h, we would get square root of 9 plus square root of 9, which of course is 6. 3 plus 3 is 6, or 2/3. So the slope of the tangent line, when x is equal to 9, after all that work, is 2/3, which of course is just the slope. Okay, now, just like in the last example, we need a point, right? So when x is equal to 9, we know y is equal to 12, so we have x value, a y value, and a slope. Okay, so let's continue this in a different color so we don't get confused. We're going to use our point slope equation to find the equation of this tangent line. So plug in 12 for y1, 9 for x1, and simplify. And as you simplify, you should get y equals 2/3 x plus 6. Okay, the second part of section 3.4, part B, begins on page 19 of your course notes, and this top part is filled in for you, but let's just follow along. It says the derivative of a function will exist when the following three conditions are met at a point. The first one is the function is continuous. Okay, if you need to, go back in your notes and review what it means to be continuous at a point. The second part is the function is smooth. Okay, now that means that there's no sharp corners or curves or like an absolute value function where there's a point, that would be not smooth. Okay, and then the third thing, at this point, the function does not have a vertical tangent line. The function does not have a vertical tangent line at the specific point. Okay? Okay. The second part says, therefore, the derivative of a function will not exist when any of the three conditions are true at a point. Very similar to the last, except we're kind of saying the opposite. So it will not exist if the function is discontinuous. Okay, it will not exist when the function has a sharp corner. Okay, and then lastly, if the function has a vertical tangent line, the derivative will not exist. Okay, so we are saying is just because f is continuous at a point doesn't necessarily mean that the derivative exists there. So it could be continuous, but the derivative might not exist. For example, like I mentioned before, let f of x equal the absolute value of x. The function is continuous at x equals 0, okay? But the derivative at 0 does not exist. The tangent slopes immediately to the left and to the right of 0 are not equal. Okay, so the slope to the left is -1, the slope to the right is +1. Those do not match. Another way of explaining this is that saying zooming in on the graph at x equals 0 does not make it look like a straight line. So the limits from each direction match, okay, but the function doesn't have a derivative at that point. In other words, looking from left and right, the slope from each direction is different. So it is not, there is no derivative there. 57. Okay, so let's look at an example. Okay, now we are on page 19 of your course notes, if I didn't mention that before. Okay, the function I of t equals 27 plus 72t minus 1.5t squared represents the eating behavior during a meal where t is the number of minutes since the meal began, and I of t represents the amount in grams the person has eaten at time t. Find the rate of change of the intake of food 5 minutes into a meal and interpret the result. Okay, let's first find the derivative of this in general for any t value. So we want to use our equation. I of t equals the limit as h approaches 0 of I of t plus h minus I of t over h. So we want to plug in our t plus h wherever there is a t in our original equation. So we'd have 27 plus 72 times t plus h minus 1.5 times t plus h squared minus our original function, 27 plus 72t minus 1.5 t squared, all divided by h. Okay, now we have some algebra to do. So we want to distribute our 72, so we have plus 72t plus 72h. Now, we also want to FOIL this t plus h, okay? So off to the side, t plus h squared is equal to t squared plus 2th plus h squared. And then I'm also going to distribute our negative 1.5. So we get minus 1.5t squared minus 3th minus 1.5h squared. And now we can also distribute our negative here. So minus 27 minus 72t plus 1.5t squared. This is long, so we at this point are really hoping that some things start canceling themselves out, and it looks like they do. So we have 27s cancel out. We have a negative 1.5t squared and a positive 1.5t squared. Let's see, plus 72t minus 72t, and it looks like that's about it. So next step, the limit as h approaches 0 of 72h minus 3th minus 1.5h squared. And as you can see, an h will cancel out of each term in the numerator. So we would have 72 minus 3t minus 1.5h. So if h is approaching 0 and our limit of a polynomial, we can just plug in our limit value. So we get 72 minus 3t. So this is the instantaneous rate of change, the derivative, the slope of the tangent line, all of those things at a given t value. So we can write it more officially. I prime of t equals 72 minus 3t. So part A. Ask us, find the rate of change of the intake of food 5 minutes into a meal and interpret the result. Okay, so what we want to do is actually plug for part A. We want to plug, we're saying t is equal to 5. So we want I prime of 5, 72 minus 15, right? If we 3 times 5 is 15, so we get, losing myself here, 57. Now, if we go back and read the problem, I of t represents the amount in grams the person has eaten at time t. Okay, so we want to know the rate of change of the intake of food. Okay, so what does this mean? If the derivative at t equals 5 is 57, right, this means the rate of change is 57 grams at time t. Okay, 57 grams per minute. Okay. Okay. Part B. Verify the rate in which food is eaten is 25 minutes into the meal. So part B, we want to find I prime of 24. So we are simply plugging in 24 into the derivative we just found, and it is 0. Okay? So that means the rate of change is 0 24 minutes into the meal. The amount of grams of eaten at a certain point is no longer changing. So how useful is this function after 24 minutes? Well, logically, it is not useful after 24 minutes anymore because the food is gone. Okay, there's no longer any food being eaten. There's no longer any rate of change. The rate of change is 0. So what should the domain for this function be? Well, the domain then should be from 0 to 24. So from 0 minutes to 24 minutes.